Hello, we're working on chapter 3, and in section 3.2 we're going to be taking a look at the calculus of vector valued functions. So let's get to it. Okay, in this video we will be looking at the first objective where we express the derivative or find the derivative of a vector valued function, and then we'll hit the other objectives a little bit later on. So just to remind ourselves, a vector valued function r of t would be some vector that would have x of t, y of t as functions in 2 dimensions, but if you're in 3 dimensions we have a third function, z of t. So what we could do is we can imagine this thing in 3-dimensional space, x, y, and z. That this would be some sort of some curve or something like that in 3-dimensional space. Now the derivative is defined to be this. We have r prime of t is equal to the limit as delta t approaches 0 of r of t plus delta t minus r of t divided by delta t. So it's the same sort of picture that we might have seen, except we are looking at vectors, vector valued function. So we imagine that the vector valued function is going to give us an output of a vector in 2 or 3 dimensional space, and we can imagine that at some point we have r of t. Let's put r of t over here, and so we can think about that as a vector from the origin. And then we have an r prime of t, or I'm sorry, we have an r of t plus delta t. So with a small amount of movement, we have r of t plus delta t. And so we have another vector. Now when we subtract that, as is written in the numerator, we get the head minus tail. So we get this vector over here. And then what we're doing is we're figuring out what happens as delta t gets closer and closer to 0. So it seems like this thing would be shrinking. But surprisingly, since this is going to go to 0 and this is going to go to 0, then your result is going to be indeterminate until you actually find out that the length of this vector is not necessarily going to be 0. So there's some interesting things that happen when you have an indeterminate form. You come out with something that actually is non-zero. So here's another statement that talks about the limit of this derivative function, or the limit of this definition for the derivative. So provided that the limit exists, this is going to be saying that r prime of t exists, and so r itself is differentiable for an open interval. And just this technicality that we won't be dwelling on too much, but if we want differentiability for a closed interval, then we also want to make sure that those limits exist at a and b. Since we're only defining from the inside, then the limit of a coming from the right side and the limit of b coming from the left side. Again, just some technical details that we don't need to worry about. The main thing that we need to get out of this is really the derivative of a vector valued function. Instead of using the limit definition, we are going to jump directly to the shortcuts. And the shortcut is that the derivative of a vector valued function is going to be the derivative of each of those components. And done separately, you take the derivative of the components and then you'll have your derivative of the function. Okay, so that's really the bottom line. Let's take the derivative of this vector valued function. We have r of t is equal to 6t plus 8 in the I direction and 4t squared plus 2t minus 3 in the j direction. So if I were to take the derivative of this, I will call this r prime of t, and I'll even switch notation to use the angle bracket. And the derivative of 6t plus 8 is 6, and the derivative of 4t squared plus 2t minus 3 is going to be 8t plus 2, and then there's my derivative. I'm done. Okay, let's just do one more example for good measure. To find the derivative of this, we take r prime of t is going to equal to, now the derivative of the first component is going to be a product rule. So it's derivative of the first times the second plus the first times the derivative of the second. So that's just the derivative in the first component. And then now we have the derivative of the second component. So again, it's a product rule. Derivative of the first times the second plus the first times the derivative of the second, and derivative of cosine is negative sine. So I'll put a negative sign in front of all that. And then finally we have a negative e to the 2t times 2, and that is the derivative of that last component. So here are your three components that make up your derivative vector, and that's it. Okay, so it's pretty straightforward, and just taking the derivative of each component and then you're good. Alright, I hope that helps. Good luck.